So good afternoon, everyone, and thank you for the invitation. I'm Bertrand. I'm a PhD student at IFP Énergie Nouvelle. I'm on my second year, and my PhD advisors are Patrick Massin and Richard Gio. Today I'm going to talk about my research work on the extended finite element method applied to porous media. So why are we interested in the study of the behavior of fracture networks in porous media? There are several applications, and the first that comes to mind might be the controversial hydraulic fracking. So that consists in injecting huge quantities of water with a very high pressure in the parent rock to create the more dense and the more extended fracture network in order to recover the more gas. In the same range of application, we can think of the enhanced geothermal system that consists in injecting cold water and then pump it back once the heat transfer has been realized. And in these two applications, the goal is to create the more dense and extended fracture network. On the other side, we have the carbon dioxide sequestration. So it's common to use the previously exploited conventional reservoir in order to inject carbon dioxide. And here the stake is the integrity of the reservoir. Fractures may be present in the reservoir seal, and then if there is a pass for the carbon dioxide, the integrity of the reservoir is lost, and we may have a pollution at the surface. So in this case, the goal is to prevent the cracks from propagating. So what we want to model is something like this: a 3D fracture network with a porous media, fluid circulation in the cracks, fractured junctions, and we also want to focus on the mechanical part of the problem. I'm talking about the fracture propagation, also about the fracture competition, so the influence of the presence of one fracture close to another fracture, and also the problem of the fractures shutting down when the two walls of the fracture are in contact. So how to handle discontinuities in geomechanics? So when we are focused on the fluid, as Benoit showed yesterday, we can have as far as a million fracture to model a reservoir. This is absolutely not possible with the geomechanics. The finite element modelization wouldn't support such a number of fractures. So here you've got an example of a basin modeling with the sedimentary horizons and the faults in red that intersects these different layers. So the cracks in geomechanics constitutes a major issue because the meshing of such geometries is very difficult for the meshing tools. So here we have a very simple model, basin model with one fracture junction, and if we zoom in the area of the fracture, we observe elements that have a very bad aspect. They are very stretched, and they ruin the conditioning of the problem, making it impossible to solve for the numerical solver. So the meshing tools sometimes fail in generating a mesh in these areas, and when they succeed, the shapes of the elements are very bad. So we prefer what we call the extended finite element method that consists in introducing additional degrees of freedom associated to discontinuous shape functions. So the discontinuity is then located in the mesh thanks to level set functions. So we've got the same crack on the left side and on the right side, meshed with the classical finite element method. So here we have elements conforming the mesh and a fine mesh at the crack tip in order to catch the singularity. And on the right side, we can use a regular mesh. The information about the fracture is directly included in the mesh thanks to these additional degrees of freedom. So we can have exactly the same behavior. Another advantage of the extended finite element is that we don't need to generate a new mesh when the crack evolves. So this is an example of a basin modeling with the XFEM. We've got the large sliding between blocks. This is the work of a former PhD student, Maximilien Schiavelis. And the initial mesh is only constituted of hexahedrons. So now I come back to the initial problem, and here are a few notations. The domain, the porous domain, is noted omega. There is a pore pressure inside this porous matrix, denoted P. In the fracture, we have also a fluid whose pressure is noted P sub F, and fluid fluxes coming from the fracture to the porous media, so key sub 1 for the lower part and key sub 2 for the upper part. The fracture aperture or the displacement jump is noted like this. So here is a sketch of the challenging aspect of this modelization. So first we have to model the hydromechanical coupling in the porous matrix. We'll also have a look at the flow in the fractures. We'll have to take into account the fluid exchanges in the matrix and between the fracture and the matrix. We'll have to model the loads on the fracture walls. We'll have to see what goes on at the fracture junctions for the fluid. And we'll also have a look at the crack tip area. So first, hydromechanical coupling in the porous matrix. So the solid matrix is associated to the displacements, and the fluid is characterized by the degree of freedom pore pressure P. So we consider an elastic medium for the solid matrix with a porosity phi, a permeability K, whereas the liquid is characterized by a dynamic viscosity mu and also its volumic mass. So the solid is saturated by the fluid, so that the fluid occupies a fraction phi of the overall volume. So then the equilibrium equation is the following, where these terms accounts for the hydromechanical coupling. For the fluid flow in the fracture, we are only interested in the expression of the flux, and we consider the cubic law for the flux. The flow in the fracture depends on the cube of the fracture aperture and on the gradient of the pressure in the fracture. In order for the model to be fully coupled, I mean coupling between the fluid in the matrix and the fluid in the fracture, we have to take into account the exchanges of fluid. So the fluid flux in the matrix is simply modeled by Darcy's law, and so that the conservation law for the fluid in the porous matrix is the following equation. As we've just seen, the fluid flow in the fracture is given by the cubic law, And the mass conservation for the fluid flow in the interface is given by this equation, where we've got these additional terms that account for the fluid exchange between the fracture and the porous matrix. So this is a sketch that summarizes what goes on for the fluid around the interface. We've got a flux W in the interface and a flux M in the porous matrix. We've got exchanges at each of the fracture walls, but we have to impose an additional condition. The fluid pressure has to be continuous at the fracture walls. So on each of the fracture walls, we'll impose the condition P equal P sub F, on the upper fracture wall and at the lower fracture wall. If this is well posed, we should have Q equals M dot N. So the fluid flux between the fracture and the matrix should be equal to the Darcy flux at the fracture wall. So this condition is not imposed. It should come naturally. So now the loads on the fracture lips. So here are some images of cracks submitted to constant fluid pressure. So here the important thing is that we are able to catch the curvature of the crack with very few elements. And so you see the deformed shape. So the fluid in the fracture opens the crack. What goes on for the fluid at the junctions? So as Benoit showed yesterday, we can use a point rule. So this is a non-trivial result, because you also have at a point of the junction, you also have exchanges between the different fractures and the matrix. So this result is very easy to implement. It's exact for the 2D case, and it's an approximation for the 3D case. So we'll rely on this for the behavior of the fluid at a fracture junction. So here is a sketch of a fracture junction in 3D. This is the initial mesh, so only constituted of 25 hexahedrons. And if we apply a constant pressure in each crack, we get something like this. So the finer meshes has been created by the code. This is the XFEM mesh, but the approximation mesh is always this one. And now the crack tip area. For the crack tip area, we use a cohesive zone model that consists in subdividing the crack tip area in 3 parts. A free surface, where the crack is completely open. A zone which is undamaged, LC, and there is no crack or no damage in this part. And between these two, we have the cohesive zone, in which cohesive stress are opposed to the opening of the fracture. So in this zone, we will have the stress coming from the matrix that have to fight the cohesive stress, and which is helped by the fluid pressure in the crack. So the stress is the stress on the fracture wall. The cohesive stress is straightly linked to the fracture aperture. This is the cohesive stress against the fracture aperture. So we are using a non-regularized cohesive law. And once the critical stress of the material sigma sub c is reached, the damage starts irreversibly. So here is a stage where damage has been made, and the cohesive law has a lower critical stress. So the formalism we choose for the cohesive zone model has been introduced by Eric Lorenz, and we know that the use of this cohesive zone model implies loading control because of this non-monotone behavior. And for the crack propagation process, we will rely on what has been developed by Guillaume Ferté recently, which is a process that allows the propagation of cracks on non-predefinite paths for 3D models. So now I'd like to focus on some of the specificities, the technical specificities of this model. Here is an HM-XFEM element. So as you see, the summit node carries all the degrees of freedom, so the displacements U, that are also carried by the middle node. So the displacement field is quadratic and enriched. By enriched, I mean that it is an XFEM field, so it can be discontinuous over the fractures. And the summit node also carries all the other quantities, so the pore pressure in the matrix, the pressure of the fluid in the fracture, the fluxes, and the Lagrange multiplier lambda, which is associated to the cohesive law. So the pore pressure is linear and enriched. It's also an XFEM field. And the fields that are associated to the fracture, so the pressure and the fracture, the fluxes and the Lagrange multipliers, are linear, but they are also subject to equality relations to reduce their approximation space. So they are not necessarily P1, they are what we call P1, P0. Because in this example, you see the crack in red, and the summit node that are surrounding the fracture are, we create a group between these nodes, and all of the nodes that are in the same group will have the same Lagrange multiplier or the same pressure of the fluid in the crack. So this allows us to have a total of 3 different approximation spaces. So one quadratic, one linear, and one which is P1, P0. But these 3 approximation spaces are necessary to avoid oscillation in the solution, so to satisfy the LBB condition. So now just a last point, why is the pore pressure field enriched? Well, this allows the pore pressure to be completely discontinuous over the fracture. So here is a constant pore pressure in each, a constant pore pressure in each block. So this is what XFEM allows. This is a 1D example. We've got the nodes, and at the crack, we can have a discontinuity of the pore pressure and its derivative at the crack. But we want the continuity of the pressure at the crack. So that's why we weakly enforced the condition P minus equals P plus, or with this set of equation. So that at the fracture, we have P minus equals P plus equals P sub F. So this is what we finally get, and this allows us to have a nonlinear pore pressure field in the element that is crossed by the crack. So here is an example of a pressure diffusion from the fracture in the matrix. So the fracture is at the middle of the column. We impose fluid pressure in the fracture, and the pore pressure diffuses in the matrix. Now to conclude, the HM-XFEM model is very ambitious. These are very heavy elements. It requires a lot of developments. In terms of modeling a 3D fracture network, it relies on the latest advances in the extended finite element method. I'm talking about 3D quadratic elements, crack propagation with cohesive zone models, and fracture junctions. as far as now I've reached this stage, I'm able to set a 3D fracture network. I validated the hydromechanical coupling in the matrix. I'm able to have a pressure loads on the fracture walls and fluid exchanges at the fracture walls, and I'm currently working on the implementation of the cohesive zone model and of the implementation of the flow in the fracture. And the last point I want to mention, I'm developing these elements in a Cadaster, which is an industrial based software developed by Électricité de France. And it's a free software, so you can download it on the internet. Thank you for your attention. Yes.
I was looking for something, and I don't know if it is in the model or not. Is there a gapping between the rate of change of the aperture of the fracture and the mass balance? I mean, is in your fluid mass balance in the fracture, do you include the opening of the fracture?
Yes, I think so. Yes, this term accounts for the evolution of the fracture aperture for the mass conservation of the fluid in the crack. Because this is the.
And how does this depend on the pressure in the fracture?
Because W. You mean the fracture aperture? Because of the cohesive law.
So let's say it's already open.
Yes.
The pressure in the fracture.
Mm-hmm.
The result of that is opening the fracture.
Yes, it's opening the fracture.
But the pressure is continuous. Just the mass.
Yes, we have a dynamic effect. So, and in the porous matrix, the hydrostatic pressure term is multiplied by the Bio coefficient, which is not necessarily equal to 1. So the pressure load coming from the fracture might be higher, and but if it's equal to 1, in the end the fracture will shut down, which is physical.
Typically, when you have this kind of rigid elements, you need the tracking algorithm. What algorithm are you using to follow the track?
For this, I rely on the work of Guillaume. I've not reached this stage as far as now, so I can't tell you much about it. But it's based on the use of the cohesive zone. He computes the coefficients K1, K2, and yes, fracture mechanics.
You have discontinuous for pressure.
Yes.
And you impose the continuity with some random multiplier.
Yes.
Other model like MOS, for instance, they have discontinuous fluxes and continuous pressure. And why do you find this way is more convenient?
I think in this way we don't have to introduce different shape functions, so we just have to multiply it by the if side function, the classical shape function, and your question was why don't we introduce directly this kind of shape function? Yes, my PhD advisor, which is a specialist of this question, told me it would be easier. And
the principle of authority. If you want my advice, the principle of authority since Aristotle is
because we would need to have a discontinuity in the derivative of the pore pressure. And this is more difficult to implement. Yes?
Okay. More questions?
Most of the time you consider that there is a lag. So it means that the fluid, that's what is dry, there is no
Yes, the fluid lag.
So but in your case, you always consider that the gravity is saturated.
Exactly, yes. So we can even have a negative fluid pressure, which is annoying, but if we take the data of the model, we can prevent this phenomenon from happening if we set the right parameters. Yeah.